Well, good morning, everyone. It's a great pleasure to be here and to see so many people in the audience. I wasn't sure how many people were going to take the time before the start of a new semester to attend. As Martin said, I'm Professor Angus Wilkinson. I'm with the School of Chemistry and Biochemistry and also the School of Material Science and Engineering at Georgia Tech. Now, the program says I'm going to be talking about in-situ studies, which is an enormous topic. I'm narrowing things down a little bit. I will be talking about non-ambient diffraction studies of negative and low thermal expansion materials today. Nearly all of this work is actually done using synchrotron X-rays and neutrons, but I'm going to try and put my work in the context of what might have been possible if we had X-ray equipment that's just arrived a few years ago and this work was actually done. Okay, so some starting comments on synchrotron X-ray versus lab X-ray equipment. Those of you that have done any synchrotron experiments probably recognize that this is a wonderful source of very bright radiations. You can do very quick measurements. You can get wonderful signal to noise ratio data. You can pick whatever wavelength you want within reason, which means you can use short wavelength X-rays to punch through bulky bits of sample environment. Many wonderful things about synchrotrons. Several big downsides. You have to travel, you get very limited beam time. If your experiment doesn't work out, you may have to wait 6 months. You may never get another opportunity to repeat that measurement. Whereas if you can do things in your home lab, if you have a well-equipped lab like we do now, you can repeat experiments more or less at your leisure. You can make measurements over extended periods of time. And something that I think is important, but probably isn't obvious to you, is that that equipment is stable. Your copper or molybdenum K-alpha X-ray tube puts out the same wavelength today as it did yesterday and 3 months ago. That can be a problem with synchrotrons. I'll point that out as we go through some of my example studies. So the work I'm actually going to present was done either here at the Advanced Photon Source, Argonne National Lab in Chicago, or an Oak Ridge National Lab using the Symposium neutron source or high flux isotope reactor. Wonderful facilities. When we're doing variable temperature studies, which is one of the things we very commonly do for the synchrotron, we may be using a device like this. This is a cryostream. Those of you that do single crystal diffraction studies have probably used this. Basically, you have a jet of nitrogen gas coming out of this nozzle. You can control its temperature, and we are passing it over a capillary of powdered sample. Change the temperature of the gas, you change the temperature of the sample. It's very easy. Synchrotron experiments are nearly always done with capillaries these days. Nice geometry in the sense that the sample is contained. You don't have to worry usually about moisture or oxygen exposure. But you don't necessarily have super accurate temperature control. This is a furnace that we've used a lot with the synchrotron, rather crude compared to lab-based furnaces. You can see a wire-wound heating elements here either side of a capillary containing your sample. And you can collect data very, very fast. These are powder diffraction data. Each one of these streaks, whoops, hang on. That was very quick, is a Bragg peak. You can see this group of Bragg peaks splitting apart as we cool, as we reheat, they merge. You see some change in position due to thermal expansion. You get a picture here based on about 500 powder diffraction patterns collected, a few seconds exposure each. Very rich picture of what your sample is doing. Very nice. Okay, so in addition to high temperature, variable temperature experiments, which could be done in many cases in the home lab, or almost equally well if you have the right equipment. We do high pressure measurements as well. Common mode to do that is the so-called diamond anvil cell. This is a diamond anvil cell. It's about the size of my fist. At its core, we've got a pair of diamonds squeezing on a gasket, basically a metal washer with a tiny hole on it. Your sample is in this cavity. And X-rays are going to go through the diamond, through the sample, be diffracted, side. Okay, so we're going through 4 or 5 millimeters of diamond here. Our sample cavity is 300 microns across. It really helps if you've got small, bright beams of high energy X-rays to do this. This should not be readily done in home lab. Much better done. All right, so that's background to methodology, some background to the low and negative thermal expansion materials I'm really talking about. One might wonder, why do you care about thermal expansion? If you're an engineer, that's probably obvious. If you're a chemist, physicist, maybe less obvious from an application standpoint. But it turns out that thermal expansion is a really important engineering characteristic. And if you're building a telescope mirror, or you're building a fiber optic communication system with diffraction gratings in it, it's really annoying if the diffraction grating spacing changes because some component expanded as the temperature changed, because your system doesn't work any longer. So being able to make components that are low in thermal expansion gives you the stability you need for your device to work properly. Now, we actually we work a lot on negative thermal expansion materials, materials that shrink when you heat them. And they have the same problem as positive thermal expansion materials. Dimension change in temperatures is no good either way. So you might ask, well, why do we work on negative thermal expansion materials? And the real answer is because it's fun, it's different. But the technological answer is that in principle, you can use contraction on heating to compensate for expansion on heating, perhaps by making a composite, blending two different materials together to get characteristics that are somewhere between the two components you put into that composite. But if you do that, as one material expands and another contracts in the composite, you get stresses in that composite that can actually cause problems. So when we study the thermal expansion materials, in addition to making variable temperature measurements, we make high pressure measurements. We look at their response to stress, or at least hydrostatics. All of the work I'm going to talk about today is on rhenium trioxide structured materials. These materials consist of corner shared octahedra. So think of metal somewhere in the middle of this octahedral unit, and each of these corners anion, and the shared anions, the shared corners link the structure together. Now, that kind of structure can give rise to negative thermal expansion, because if you supply thermal energy, the lowest energy vibrational mode pretty much typically involves transverse vibration of these bridging anions. And when you do that, when you take one of those linear links and you cause that central atom to vibrate backwards and forwards like that, if you bend, your elbows get closer together, that structure is drawn in. So a large amplitude transverse motion here gives rise to contraction of the structure, negative thermal expansion. At least that's the picture. Now, you can see a date on this, 1998. I was actually quite a young assistant professor at that point, a long time ago. When that cartoon came out, actually, the surprising thing about it was that no material with this structure was actually known to display negative thermal expansion. So it was a compelling cartoon with no real examples to support it. About 10 years after this, I took that as a challenge and started to work on rhenium trioxide structured materials in an effort to find one that would actually show negative thermal expansion. And after a bit of looking, we initially settled on scandium trifluoride. Just bought it, even though we're a chemist, didn't make it, we actually just went out, bought it. Very convenient, and we measured using powder diffraction, lattice constant for the function of temperature. Lattice constant, this is temperature. Low temperatures, we're using a helium cryostat with neutrons, because helium cryostats are readily available at neutron sources. No better reading than that. At intermediate temperatures, we were using our cryoscreen, so minus 100 Kelvin up to 500 K. Slightly higher temperatures, we use the wire-wound furnace I showed you a picture of. And to get to even higher temperatures, we partially destroyed a very expensive link furnace with our sample in a platinum tube. And we see continuous contraction from 10 Kelvin to over 1,000 K. This material's just going, not literally, it's actually a very slight contraction. and then above 1,000 Kelvin, some expansion. So that was the first time that anybody presented real evidence that that cartoon made sense for reintroduced theories. I said that we study our materials under pressure. We did this for scandium fluoride as well. And here we're using this, give you some scale. That's about that round, made from aluminum metal. It's about this long. You have to put a beam if you're going to do diffraction to an inch of aluminum. Wow, you're going to be really annoyed with that. To an inch of aluminum metal. So neutrons are good for that. Not so easy with X-rays, absolutely impossible with lab-based X-rays. But we can do diffraction in this gas pressure cell. We can cool it at the same time. We get a phase diagram out, and you can see standard fluoride. We maintain this cubic structure that gives negative thermal expansion up to about 7,000 atmospheres pressure. But on cooling, that phase boundary drops. And the time you're at 50 Kelvin, somewhere between 1,000 and 2,000 atmospheres, the material is kind of unstable with respect to the structural phase transition. And you may say, well, 1,000 atmospheres are high pressure, no big deal. Actually, it's not. You can generate 1,000 atmospheres pressure on something easily. Just take a pestle and mortar and grind. That's the kind of stress levels you get, or actually higher. So these kinds of low pressure phase transitions you can generate in composites due to one material expanding and contracting. You can get just. After a while, we moved on to other things. We did the obvious thing for solid state chemists. Let's swap out 3+ scandium ion for 1-to-1 mixture of a 2+ 4+ ion, calcium zirconium fluoride. Very similar structure, alternating calcium and zirconium centered octahedra, nice cavities, open space in between these octahedra. We made the same measurements. We looked at thermal expansion, so the neutrons for low temperature in the helium cryostat, cryostream for intermediate, Weyerland furnace, continuous contraction, 10 Kelvin to 1,000 K. Probably would have gone higher, but 1,000 Kelvin, this material eats its way through the few sports capillary tubes used. That's something to think about when you do high temperature diffraction. And overall negative thermal expansion that is actually much bigger in magnitude than scandium fluoride. Really impressive. So you have here a material with no d electrons on the metal, very big electronegativity difference between the metals and the fluorines. What that means is big band gap, non-optically absorbing out in the ultraviolet. Because it's fluoride, soft vibrational modes, optically non-absorbing to mid-infrared. This material has a really big window of optical transparency. You process it right. It is processable as a ceramic, as well as showing negative expansion. What happens when you squeeze it? Oh, that's the Achilles heel for this material. Bad things. Okay, so more powder diffraction data. Each one of these streaks, the Bragg peak from my initially cubic sample. But you can see as I go up in pressure, this Bragg peak fades out, some broad pops, this red blob here grows in. This material is becoming disordered. It amorphizes as we squeeze it above about 4,000 atmospheres pressure. That's a low pressure phase transition solid states. Okay, so illustrated two of our kind of best materials as far as negative thermal expansion goes, but both are showing strong negative thermal expansion and unwanted low pressure phase transitions. And you can ask, what can you do? What can I do to control those properties? To maybe get zero thermal expansion, to get rid of those unwanted low pressure phase transitions. Well, the obvious thing to do is to just keep swapping the metal cations. Doesn't work. Right? You swap the metal cations, things just get worse. Another thing to do is to think about that open cavity inside the structure. Let's shove something in. Right? We have all this lithium intercalation chemistry in every issue of every journal you look at these days in the guise of battery technology. Let's insert lithium into this, put something into the cavity. That will affect the vibrational motion of the fluorine. It'll give us control over properties. And to some extent it does, but now you lose that optical transparency. You reduce the metal you got to your electrons. So that's not a good idea. Let's shove something else, maybe neutral into the cavity. You can put helium gas into that cavity. It takes 5,000–6,000 atmospheres, so it's not a good idea. Let's do something radical. Let's take that corner shared structure and change it. We will convert selectively some corners to shared edges. That will reduce the flexibility of the structure. It will give us tunability. How do we do that? Well, it's actually known. It's been known since the 1970s how you can do that for some rhenium peroxide type fluorides. So this is the general recipe. Take our all corner shared structure, add excess fluoride and bake. And you can convert those corner sharing motifs to edge sharing motifs. So that was what we proposed. So that's where the extra fluoride has gone. And when you do that, this very flexible link becomes flexible now in only one direction. It's like a raw hinge. You can only bend in one direction. So how do we make that real? Well, we looked at lots of systems. The one where we had most success with magnesium zirconium fluoride. You take as your parent stoichiometric MgZrF₃. You replace some of the magnesium by zirconium 4+ to keep charge balance. You need extra fluoride with 2x. So that's our extra fluoride dialed in. Now, there's more than one way you can incorporate that stoichiometry into this basic crystal structure. One possibility is that all of these fluorides just fill corner sharing sites, and actually some of the cation sites empty. And the other possibility is what I intimated on the last slide, which is the extra fluorine goes into interstitial sites and gives you those edge sharing polyhedra. Those two possibilities have different densities. And this slide shows measured density, dark blue, against what you expect for those two possible models. Interstitial fluoride or cation vapors. You can see this stacks up really well as an anion interstitial material. It's nice. That doesn't mean that we really have edge sharing polyhedras. What's the evidence for that? We turn to another tool in the powder scattering kit bag, and we take scattering data out to very high Q, small d spacings, Fourier transform it, and get a pair correlation function. So these are X-ray and neutron pair correlation functions, and you see a bunch of peaks. Well, everywhere you have a peak like this one, you have a pair of atoms in that solid separated by the distance that peak's at. So this peak is at 2 angstroms. That's telling you I've got pairs of atoms separated by 2 angstroms in my sample. This case is a metal fluorine bond. This method works even for glasses and liquids. You don't have to be crystalline. Now, when I look at these data and I change the amount of excess zirconium and excess fluorine, you can see in the X-ray panel this peak growing here at 3.6 angstroms. Not very obvious in the neutron cases. We take away from that that this peak is probably associated with a pair of atoms with high atomic number. X-rays are more sensitive to high atomic number elements, low atomic number ones. Neutrons are somewhat agnostic. Okay, so this is probably telling us we have a pair of zirconiums, our heaviest element, separated by 3.6 angstroms. How do we interpret? Well, this is my proposal, right? Corner to edge sharing. In this structure here, the center to center distance is roughly 4 angstroms. But when you convert to an edge sharing unit, the center to center distance is shorter. And if you look at crystal structures of beautifully ordered, fully stoichiometric ordered solids that contain zirconium-centered polyhedra like this, the center to center distance is, yes, 3.6 angstroms. We take that peak as strong evidence that we are converting locally corner to edge sharing polyhedra. What does that give us? Does it give us the control we saw? Yes, it does. So this is unit cell volume measured by powder diffraction over a range of temperatures. Low temperature is neutron, high temperature is bright green X-ray. You can see for small amounts of excess fluorine, we have negative thermal expansion. And as we dial in more, we go to positive thermal expansion. And if you happen to pick x equals 0.2 which we didn't, sadly, we would expect zero thermal expansion at room temperature. So we've got control through the use of excess fluorine changing the local structure of the material. But there are some flies in the ointment. Have a look at this panel. So this is lattice constant versus temperature on heating and cooling for one of our samples. You can see they don't reproduce. Now, normally I would say, oh, we have an experimental problem. But we have the internal standard in this sample because we've seen this kind of thing before. And our internal standard, which was silicon, reproduced beautifully on heating and cooling. The experiment was fine. The sample really is non-reproducible on heating and cooling. And that's because these are disordered materials made at high temperature, cooled to room temperature, left there for a month, taken to the synchrotron, measured. Okay, over a month, that disordered local structure, which was pseudo-equilibrium at high temperature, has changed, is relaxed. When we warm it up, changes again, and doesn't change fully back on cooling. It's the hypothesis. Okay. Now, sometimes when you see non-reproducibility, it really is a problem with the equipment. So another data panel. Here, my silicon lattice constant on heating and cooling doesn't reproduce. What's going on here? Well, it's another thermal expansion problem. Took us a while to figure this out, but we were making measurements the day after or the day of a restart. Synchrotron had been down for maintenance for a couple of days. There'd been no X-ray power on the mirrors and on the monochromator for the beamline for 2 days. Everything was cold. Now you put a lot of X-ray power onto your optics. The monochromator, which is what is delivering a well-defined wavelength you heard for you, starts to warm up. It takes a long time in some beamlines to come to thermal equilibrium. This beamline apparently in the order of 12 plus hours. So as it warms up, as it comes to an equilibrium lattice constant, the wavelength drifts. And what you're seeing here is the effects of the change in wavelength as our monochromator comes to thermal equilibrium after being cold and exposed to high X-ray powers once the synchrotron is back running. If we were using the lab equipment for that, I wouldn't have to worry about this. Right? The wavelength from my X-ray tube is the same today as it was yesterday, will be tomorrow. What about high pressure transitions in this material? Well, actually, our trick actually solves those problems as well. So these weird looking panels, so again, powder diffraction patterns, each one of these lines is a bright peak. There are hundreds of diffraction patterns put together so that you can see how these peaks evolve as you increase pressure. So this is my pressure axis. And you can see this first peak of my initially cubic sample splits in this case at about 1 gigapascal, 10,000 atmospheres. That's already slightly off stoichiometric. Pure NGZRF₃ would show that splitting at about 5,000 atmospheres. As we dial in excess fluorine, you see this transition moves up to 4 gigapascals, 40,000 atmospheres. It goes away, or at least it moves out the window where we care applications. So by adding excess fluorine, we control thermal expansion, we get rid of the unwanted high pressure phase transitions. Things are largely good. So you can ask, can we use this trick for other systems? And the answer to that is, in some cases, yes, but not always. So we spent quite a bit of time looking at this system. So we're putting in excess fluorine, but we're doing it now by replacing zirconium 4+ by niobium 5+. We go through the whole same set of measurements. Measure density. Let's make sure the fluorine is going in an interstitial site. Yes, it is. The density measurements indicate that that fluorine is going in interstitial. We do the pair distribution function studies. This is measure scattering data out to really tiny d-spacings, Fourier transform it, and look for peaks in the pair correlation function that might indicate the presence of edge shared polyhedra. So we look at 3.6 angstroms and nothing. Interesting. So excess fluorine in this system does not give us a corner to edge sharing conversion. We should really have expected that looking back. So, does it give us control over thermal expansion? Well, no, and really it shouldn't, because we're not converting corners to edges here. It's still basically a corner sharing network with some interstitial fluoride in somehow. What it gives us is a mess. So heat and cool doesn't reproduce. This is this local structure relaxing as we warm up. Complete mess. And you'll notice negative thermal expansion for x equals 1/4, and negative thermal expansion for x equals 0.5 on this second cycle, this cooling cycle. And I'll show you x 0.75 later, negative thermal expansion. Basically, the excess fluoride once there at interstitials is not taking us from negative to positive thermal expansion. Okay, well, what happens if you do multiple cycles? This is the x equals 0.75 sample. Being made high temperatures, it's been sitting around the bench for a month. We cool it down, we warm it up. This is what its lattice constant does. We cool it, we warm it, we cool it. Okay? It's just that first cycle, that heating after sitting on the bench for a month, where you see weird stuff. After this, it reproduces, but it's still negative thermal expansion, even though we have lots of excess. What happens to your high pressure behavior? Well, you probably guessed, nothing much. You still have unwanted low pressure phase transitions. You see the splitting here, characteristic of a cubic to rhombohedral transition in the material. No matter how much excess fluorine you dilate, that occurs at about 7,000 atmospheres. Okay, so some conclusions. At least in the case of magnesium zirconium fluoride, you really can get great control over thermal expansion using this approach of adding excess fluoride, converting corner to edge polyhedron. But it is not a universal strategy. You have to think carefully about the systems you choose to use this on, as illustrated by our work there. So I didn't do, actually I did do some of that work, but most of it was done by students. And I've reached back into ancient history today. The scandium fluoride work was done by Ben Greff and collaborator Ken Martin. That's actually a 2008 photograph from our original scandium fluoride experiments. Ken was a Louisiana native. He'd never been to Chicago in winter before. This was January, didn't bring a coat. But probably he will take a coat to Chicago every time he goes. And that's that. Okay, calcium zirconium fluoride work done by this guy, who was an undergrad with me at the time, Justin Hancock. He's actually now a postdoc somewhere in California. And the later work on the excess fluoride done by Sam Baxter and Brett. Hey, well, thank you very much for your attention, the opportunity to speak here today. And if we have a few minutes, I'd be happy to answer some questions.
Do we have any questions? Is there an intuitive reason for why the fluorine prefers to generate anion interstitials versus cation vacancies?
That's an interesting question. I think, so thinking on the fly, it's not something, sadly, that I've actually thought about before. I mean, zirconium actually, in fluoride materials, typically does want a higher coordination number than 6. Okay? So that kind of open ReO3 structure built out of octahedra is at some level entropically favored. And I have some other work that I'm just about to publish where I could show you some data to support that. So I think what's really going on is that this is a way of the zirconium actually achieving its preferred higher coordination numbers. Because if you were cation interstitial, it would all still be 6. And that's probably why when we add X, that's one of the reasons we add excess iota, maybe things. But yeah, it is, I don't know whether I said it explicitly, but in the edge shared units, the proposal is that you have zirconiums in the centers of both of those polygons. So it's really an edge shed between two CRF7 polyhedrons. David, you were going to ask something?
Yeah, a roundabout question. I know there are a lot of off-the-shelf things you can buy widgets for in-situ measurements. And I guess I can microphone that I won't yell.
In a beamline, which has infinite resources, you can sort of create, I think, whatever custom experiment you want with temperature and pressure. So I guess my question is this, with that sort of introduction. When you're coming up with your experiment, are you coming up with your experiment with the limitations of the tool set you're going to? Or do you think of an experiment that might have some exotic condition and see if you can custom make something to meet the measurement conditions that you need? Does that sentence sort of question sort of make sense?
Yeah, that makes perfect sense. And the answer is both. Okay. So normally you want to do an experiment that uses a piece of sample environment that exists. You know it works. People know how to use it. Okay. So everything I talked about today, the neutron high pressure gas cell, the wire-wound furnace, the cryostream, they were all pretty well tried pieces of equipment. Something I didn't talk about today, we did a lot of variable temperature, so above ambient, high pressure experiments in the kind of space 0 to 4,000 atmospheres, 0 to 200, well, 25 to 250 centigrade. And in that case, we built custom sample environment. We bought commercial grade 5 titanium tubing. We built heaters. We built a pump. We put internal collimation into the pressure vessel. We spent a lot of time and money building custom environment. So it depends. If what you want is available, you can meet your needs with what's out there, you're going to use it. But sometimes you build your own. And one of the wonderful things about synchrotron X-rays is that you're not as constrained as you are in the home lab. If you need to go through a centimeter of stainless steel with an X-ray beam, you can. You just need to get a high enough energies to do it.
Thank you. Any additional questions? Thank Professor Wilkinson again.